This is Physics 1020 and 1090. The lecture is for Wednesday, April 1. We're in chapter 27 about quantum physics, and here in this first video we're going to talk about X-rays, how X-rays were discovered and how they were used to do Compton scattering. First, how were X-rays discovered? Well, William Röntgen was the discoverer of X-rays. He was a German scientist. And right before the turn of the century, before the beginning of the 20th century, 1895, he made this discovery. So what he was doing is he was starting with a cathode ray tube. This is something a lot of physicists were working on at the time. A cathode ray tube is basically you take a glass tube, take all the air out so it's a vacuum inside, and inside you have what is basically a capacitor. And you charge the capacitor up, one side negative, one side positive. Now, on the negative plate, sometimes, especially if this is a very hot plate, you can have electrons come off of the plate and get into the space in between the two plates, in which case they experience an electric field which causes this electron, it's repelled by these negative charges, to accelerate to the right. And normally it would accelerate over here and hit the positive plate. However, there is a hole in the positive plate, so some of the electrons that are going straight at that hole will pass through. And what you've created is a very high energetic beam of electrons. So the cathode ray tube allowed you to get an energetic beam of electrons. And that's what Röntgen was initially studying. Now, as electrons come out, some of them will pass right through the glass. Sometimes they interact with the glass and create a little bit of light. Röntgen, for whatever reasons he was studying, wanted to use a very dark room, and the light was annoying to him. So he put some bunch of cardboard around the cathode ray tube to block all the light. Now, we've talked in the past about the scientific method. And oftentimes in science, you make a hypothesis and then you test the hypothesis with an experiment, and it's a very classical scientific method. Sometimes it doesn't work like that. Sometimes you just get lucky and you stumble across a discovery. This was the case for William Röntgen. He covered up, got rid of all the light, but then he noticed that there was this fluorescent screen over on the other side of his room, which kept glowing whenever the cathode ray tube was on. Now, what's a fluorescent screen? That is when something hits it, either a charged particle or a photon, it will give off visible light. So it kind of glows, it's fluorescent. So what he found is even no matter how he covered up the cathode ray tube, there was something, some particle, some thing, he called them X-rays because he didn't know what they were, was coming over here and making the fluorescent screen glow. So he tried a bunch of experiments. He even went so far as to take a piece of lead and hold it between the cardboard and the fluorescent screen. And what he found on the fluorescent screen, first of all, the lead made it darker, so he didn't see the fluorescence, but he also could see an image of his hand holding the lead. And what's more, he could see the bones inside his hand. So, wow. So he got his wife, and his wife came down. There's a very famous picture of her hand with her wedding ring, and on it you can see the bones quite clearly in her hand. So Röntgen announced this in 1895, and the whole idea caught on like wildfire. You might be surprised that in those days when they didn't have the internet and ways to transfer information, it was surprising how fast it went through the scientific world. But everybody started working on X-rays, and it became the big thing. So Röntgen's discovery of X-rays, at the time it was unknown what they were, but we now understand they're just a form of electromagnetic radiation with a very high energy photons, very short wavelength electromagnetic radiation that Röntgen discovered. Okay. Let's talk a little bit about how X-rays are produced. Nowadays, X-rays are produced. You start again with electrons, high energy electrons that you got through some method of speeding up electrons, and they bang into this piece of tungsten here. And in some cases, X-rays are given off, or some of the energy gets transformed into X-rays that are given off. This is often called Bremsstrahlung radiation, which is the German word for braking radiation. Remember, when we talked about electromagnetic theory, we talked about how charges, when they're accelerating, give off light. Well, that's exactly what happens here. These electrons are moving very fast. They hit the tungsten, they slow down, they break, and they slow down by the interaction with the tungsten atoms. And that de-acceleration, in this case, gives off energy in the form of light, but it's at a very high energy short wavelength type. Most of the energy goes into heating up the tungsten, but the tungsten has a high melting point, so that's not such a big problem. Now, suppose, and this is the way, by the way, that you get x-rays for things like if you go to the dentist and get x-ray of your teeth, they get produced by a source of x-rays. It works on this same general principle. Okay, let's look at what kind of x-rays are produced. This is the intensity of the electrons versus the wavelength, kind of like what we saw with Planck's analysis. So what you find is there's two parts to this spectrum of wavelength spectrum. First of all, there's a continuous part. It starts at some minimum wavelength, goes up and then slowly down, and it changes continuously. And there's also some discrete lines here, characteristic X-rays, which we're going to talk about in a future lecture. So I'm not going to talk about the characteristic lines right now. I want to focus on this continuous part. Well, the shortest wavelength is lambda minimum. And what causes that? Well, if all the energy from a single electron, so you have an electron with charge E, and if its energy comes on, it goes through a voltage difference, delta V, like we saw in the last slide, to give you energy, E times delta V. If all that energy gets turned into one X-ray, it has hc over lambda min is the photon energy of the X-ray. So we can determine what the photon, and if all of that energy turns into the X-ray, it'll have the lowest, shortest possible wavelength, the highest possible energy for the X-ray. Now, if some of the energy comes in and gets dissipated as heat, and maybe only a little bit's given off as an X-ray, it'll have a longer wavelength, lower energy photon. And so you get this spectrum, but this is the shortest possible wavelength you could have. Let's put some numbers in to see what kind of numbers we're talking about. Typical X-ray source might charge up those electrons by passing them through 50 kilovolts worth of electrical voltage. So 50 kilovolts, an electron going through 50 kilovolts, you could say has an energy of 50 kiloelectron volts, which is equivalent to saying you have a charge times the voltage difference. So that's electrical potential energy. The charge of the electron, 1.6 times 10 to the minus 19 coulombs. The voltage is 50 times 10 to the 3, so that's 50 kilovolts. A volt is a joule per coulomb. Coulombs cancel, you get 8 times 10 to the minus 15th joule, which is equivalent to 50 kiloelectron volts. So we know what the energy of these electrons are, and we can equate that to the energy of a photon and find the minimum wavelength, solve for the wavelength, and what you get is the minimum wavelength is hc over E delta V. H is Planck's constant, 6.6 times 10 to the minus 34. C is the speed of light, and E delta V is the energy of the electron, which is 8 times 10 to the minus 15 joules. And what you get is 2.5 times 10 to the minus 11 meters, or in other words, 0.025 nanometers. So you see you're getting very short wavelength, high energy photons well into the X-ray spectrum. So this is the way X-rays are generally produced in the experimental lab and in medical applications. So let's go on and see one use of X-rays, and that's to study the Compton effect, or Compton scattering. So again, taking a historical perspective, Compton was Arthur Compton. He was an American scientist who did this experiment in 1923. So Compton is one of the early prominent American physicists, just on the leading edge of a whole bunch of American physicists. We have heard of American physicists at this time. Another one example that we talked about earlier in the semester was Robert Millikan, who did the oil drop experiment to find the charge on the electron. But Compton was one of the leading American scientists, and what he did is he took photons, in this case X-rays, and he fired them at electrons. And what happens is the electron will go flying off with a certain kinetic energy at an angle phi, and you'll get a photon will scatter off and go off with an angle theta. But the photon may change its wavelength. This is kind of surprising because you'd think a photon would have a certain electric field that's going up and down with a certain frequency, cause the electron to up and down at that frequency, which would cause the electron to radiate light at that frequency. But he found that the frequency, or in other words, the wavelength, actually changed. It got to be a longer wavelength or lower energy. So Compton was trying to explain this, and he used ideas from really treating the photon as a particle. He said, okay, I'm going to treat the photon as a particle like Einstein did. Photon has energy, hc over lambda, but he also gave the photon momentum. And that's something that was rather new in Compton's analysis. The momentum was h over lambda. So he applied conservation of energy and conservation of momentum in the collision. So this is just like colliding billiard balls. And what he found is that he could predict what this change of the wavelength of the scattered photon minus the wavelength of the incident photon is delta lambda. The shift in the wavelength was just from this simple analysis using treating light as a pure particle that obeys the rules of collisions. He was able to derive his formula, and this is another formula we're not going to derive here in class, but is delta, the change in wavelength, is h over mc. H, Planck's constant, m is the mass of the electron, c, the speed of light, times 1 minus cosine theta. Remember, theta was the direction of the scattered photon. So it's useful to, when you have a complicated equation like this, to look at some special cases. And that's what we're going to do again. Remember, equations aren't just something you take and put numbers into to get other numbers. Equations tell a story. Let's look at what story this says. Well, first of all, what happens if theta is 0? Theta is 0 would be the photon comes in and it just goes out the other side. Actually, what this amounts to is the photon missing the electron. So you could say that this is the case where the photon misses the electron. And in that case, if theta is 0, cosine of 0 is 1, 1 minus 1 is 0, it doesn't change its wavelength at all. So when you have an photon that misses, it just goes right on through with no change in wavelength. So look at the other extreme. Theta is 180. That is, the photon comes in and then scatters directly back. 180, cosine of 180 is minus 1. 1 minus a minus 1, that's 1 plus 1 or 2. You end up getting the change in wavelength is 2h over mc. So here's a picture of what happened. A high energy, high frequency, short wavelength photon comes in, hits the electron. This is before the collision happens. After the collision happens, the electron goes flying off in one direction, the photon comes back in the other direction with a longer wavelength. Some of its energy got given to the electron. You can also have cases where the photon comes in and the electron goes off in another direction, say 90 degrees. What happens there, 90, cosine of 90 is 0. You just get the delta lambda as h over mc. So we see this quantity h over mc is really important for this phenomena to happen. So let's see what h over mc is. It's called the Compton wavelength. The Compton wavelength, h over mc. Again, h is Planck's constant. So this is a quantum mechanical effect because Planck's constant is in there. C, the speed of light, so it has some relationship to relativity in light. M is the mass of the electron, which we haven't really talked about. So if we put numbers in for h over mc, which, by the way, this has to have units of meters or length because it's equal to a delta lambda, which has units of length. So h is 6.6 times 10 to the minus 34 joule second. M, the mass of the electron, is very small, 9.1 times 10 to the minus 31 kilograms. That's even small by elementary particle standards, much less than the mass of an atom. And C is 3 times 10 to the 8th meters per second. That's the speed of light. Do the calculation, you get 2.4 times 10 to the minus 12 meters, or 0.0024 nanometers. Now remember, the size of atoms is about 1/10 of a nanometer, so it's significantly smaller than the size of an atom. Now this quantity tells you how the wavelength changes. So if you were using visible light, which had a wavelength of, say, 500 nanometers, then the wavelength would change by just a negligible amount. It would change from 500 to 500.0024. You wouldn't even notice it would be lost in the experimental noise. But if you're using X-rays, where they have a wavelength of 1/10 or even less of a nanometer, then this shift in the in the wavelength as a percentage is much larger. So Compton was doing this experiment with X-rays. He really needed X-rays to do the experiment, and he was able to confirm then by experiment this idea that you can treat the X-rays. You can treat the X-rays as having energy and momentum. Now, occasionally, since we're taking kind of a historical perspective, I'd like to read a little bit from The Making of the Atomic Bomb when it's relevant. I want to read a couple paragraphs about the Compton effect because here Richard Rose has some interesting things to say. In 1920, Compton writes, he accepted a professorship at Washington University in St. Louis, a small kind of place, to get out of the mainstream of physics so that he could concentrate on his scattering experiments, which he was then extending from gamma rays to X-rays. He scattered X-rays with a graphite block and caught them and measured their wavelengths, Moseley style. We'll talk about Moseley in a later class. With a calcite crystal X-ray spectrograph. So he measured the wavelength. He found that the scattered X-rays scattered by the graphite came out with wavelengths longer than their wavelengths going in. By the way, the graphite was just a source of electrons. As if a shout bounced off a distant wall, came back bizarrely deepened to a lower pitch. If X-rays, light, were only a motion of the waves, then their wavelengths would not have changed. Compton had in fact demonstrated in 1923 what Einstein postulated in 1905 in his theory of the photoelectric effect, that light was a wave but also simultaneously particle, photon. An X-ray photon had collided elastically with an electron as billiard balls collide, had bounced off and thereby given up some of its energy. The calcite crystal revealed the energy loss as a longer wavelength of X-ray light. Arnold Sommerfeld hailed the Compton effect, elastic scattering of a photon by an electron, as probably the most important discovery that could have been made in the current state of physics, because it proved that photons exist, which hardly anyone in 1923 yet believed, and demonstrated clearly the dual nature of light as both particle and wave. So even though Einstein had done as an experiment, he hadn't convinced everybody, and it turns out that Compton was the one who really convinced people about this dual nature of light. Okay, I want to go on and talk a little bit more about the dual nature of with particles and waves, and talk about Louis de Broglie and the de Broglie wavelength. De Broglie was a French scientist. He came up with this idea in 1924. He actually proposed this in his PhD thesis, so it was a hypothesis, which was then tested and shown to be correct. So he said light has both wave properties and particle properties. So he thought, well, maybe electrons have both wave properties and particle properties. So electrons might also behave as waves. And he, through some reasoning, associated a wavelength with an electron. What's the wavelength mean? Well, it's kind of mysterious. That's why this was an odd result. He said the wavelength should be Planck's constant over the momentum. Well, that's very similar to what Compton used for the momentum of a, remember the Compton used the momentum of a photon as h over its wavelength. So it's a similar type of relationship. And if you're dealing with electrons that aren't going too fast, momentum is just mv. It turns out if it's going relativistic, it's a little different, but it's mv. So the wavelength should be h over mv. So this really nails down this idea that waves have wavelength and frequency, particles have energy and momentum. Light has both wave and particle properties, and electrons have both wave and particle properties. So, being scientists, so you have a hypothesis. What do? With a hypothesis, you test it in an experiment. What experiment could you do to verify that you have a wave properties with electrons? Well, what experiment did we do to verify that light had wave properties? We did Young's double slit experiment. Let's do the same experiment, but with electrons. So this happened a little bit later, so it's kind of getting out of order historically. But here's the classic experiment, which shows really that electrons have these wave properties. You take a screen with two narrow slits in it, and you pass a bunch of electrons at the screen, and some go through the narrow slits. And then you have electron detectors, so you basically have a screen back here which detects the electrons, a bunch of electron detectors on here. And what is seen is you see interference patterns. bright, dark, bright, dark, bright, dark. You get constructive, destructive, constructive, destructive, constructive, destructive interference. So just like in Young's experiment, the interference of effects really prove the wave nature of electrons. So electrons have these wave properties, and just like with Young's experiment, you could go through and you could calculate the wavelength of the electrons, and they worked out and matched with what the Broglie found. So hypothesis to experiment to confirmation, the scientific method. These wave properties of electron have implications for the electron microscope. So what do we do with light? Light has wave properties, and we use it to make light microscopes. And the resolution of a light microscope is limited by diffraction. And you can't get resolutions that are much smaller than the wavelength of light because of diffraction effects. Same true with electron microscope. An electron microscope uses the wave nature of electrons to create images, but you can't get the resolution much better than the wavelength of the electrons. So you can take, say, electrons, they're sped up so they have kinetic energies of 10 kiloelectron volts, 1.6 times 10 to the minus 15 joules. And if you know that's the energy of the electron, you can then calculate 1/2 mv squared. We know their mass, you can calculate their speed. I do that here. The speed is 2 times the energy over the mass. Comes out to be 60 times 10 to the 6 meters per second. It seems really fast, but it's actually only 2/10 the speed of light. So most relativistic effects only become important when you get up real near the speed of light. This is fairly good. You can fairly accurately use non-relativistic mechanics. That's what allowed us to use the energy as 1/2 mv squared. So that means you can use de Broglie's analysis. The wavelength is Planck's constant over the momentum, mass times speed. Planck's constant, 6.6 times 10 to the minus 34. The mass of the electron is very small, even by elementary particle standards, 9.1 times 10 to the minus 31. And the speed we just calculated is 60 times 10 to the 6. What you get is 1.2 times 10 to the minus 11 meters, or 0.012 nanometers. So that's below that's less than the size of an atom. So electron microscopes in theory ought to be able to give you atomic resolution. In practice, they don't usually get quite down to atomic resolution, but they have extremely good resolution, much better than a light microscope. And it's again, it works because the wavelengths of electrons can be much smaller than the wavelength of certainly visible light and a lot of light that you use in microscopes. So that takes us through these ideas of the wave and particle nature of both photons and electrons. And this is going to lead then to the ideas of quantum mechanics. So in the next lecture, we'll get into more detail about some of the more modern ideas of quantum mechanics.